Hi there, welcome to your lesson on applying the Pythagorean identity. Let's begin with some big ideas though. We're in trigonometry and we've learned some big things. Let's recap some of the key things. First big thing, we have a unit circle. It is called a unit circle because it has a radius of 1 unit in length. We can see 1 unit here. Also 1 here, 1 here, 1 here. On that unit circle, we can place a point. That point has some x and y coordinate. Don't forget that the unit circle has a center 0, 0. Therefore, every location on the unit circle has some x coordinate and some y coordinate. And those x and y coordinates are either positive or y values, depending on the location. So this one here, for example, has a positive x and a positive y value. To find the coordinates of that point, we can use trigonometry. So what we do is we spin an angle from this axis in this direction. We call that angle theta. We drop a perpendicular down and we've made a right triangle. So now using basic right triangle trigonometry, we can find the location of this point by finding the lengths of these two sides. This again is a positive x value and this is a positive y value. So we know these are going to be positive values. Okay, to find that, that point, we can also say the hypotenuse is 1 because the radius is 1. So we can begin with sine. Sine of an angle is always opposite of hypotenuse, so we have y over 1. That can be simplified into y equals sine theta because the radius was 1. So now we know our y value of this point and this length here can be produced by taking the sine of this angle. We can do the same thing for cosine, or for the x value. We can take cosine of this angle, adjacent over hypotenuse, and get x over 1. Therefore, that simplifies into x equals cosine of theta. So now we know to find this x value, we just take a cosine of this angle. To find this y value, we just take the sine of that angle. And those x and y values are the location of this point. And that is a point that has both positive and x and y points, right? So if you take a sine of a small acute angle less than 90, you will always get a positive value. And if you take a cosine of a small acute angle less than 90, you will also have a positive value for that. Okay, let's say this point is in a quadrant number 2 right here. Now, it's another location. We can spin an angle from the axis here again, spin that angle, theta, join to the point, drop a perpendicular down. We have a right triangle again. Now we have an obtuse angle greater than 90. What happens with this one? Well, in this case, we're going to have a negative x value because we can see that on this triangle. This is a negative x value. We're in the negative x values here. And this is a positive y value. So that point will have a negative x value and a positive y value. That makes sense. The location of that point tells us negative, positive. And that also tells us that if we take a sine of this obtuse angle, we will get a positive value because sine represents the y value. And if we take a cosine of an obtuse angle like this, we'll get a negative answer because that's a negative x value. Okay, next, going to the third quadrant, the point is here now. Spin a bigger angle like that, connect to the point, drop a perpendicular to the x-axis, we have a right triangle. Now we have a negative x value and a negative y value. Both are negative. Therefore, sine and cosine of this large angle greater than 180 will produce, both of them will produce negative answers. So we have a point that is negative, negative here. Finally, we go to the fourth quadrant. The point is there. And now we take a very big angle, spin it from the axis again, draw that connect, drop the perpendicular to here, right triangle. This is a positive x value and a negative y value. Therefore, sine of this large angle will give a negative answer and cosine of this large angle will give a positive answer because those are x and y points and we have a positive x, negative y. Please notice in the upper half we have a positive y value both times. And in this case, these points are the same y location, so they have the same positive y value. And that tells you the sine will always be positive there. And now notice on the right side here, we have positive x values for both because this is positive x values here. So those will both, cosine will produce positive values on that side. Anyway, important things to know. Let's jump from there. So to recap these key things about trig, we have a right triangle sitting in our unit circle, hypotenuse of 1. The y value is given by sine, the x value is given by cosine, and that's a coordinate here. We know also that tangent of theta equals sine theta over cosine theta. So remember that rule. We also learned that the equation of this circle is x squared plus y squared equals 1. Therefore, it can be rewritten like this because we know x is your cosine values and y is your sine values. So there we have that. That simplified gives us this, which is called the Pythagorean identity. It is a rule that works in trigonometry. Sine squared plus cos squared equals 1, and it comes from the fact that sine and cosine are just your two legs of that right triangle. Okay, we're going to use this identity now and see how we can apply it to some problems in trig. So first, before looking at that, let's go online for a moment and take a look at the unit circle. So here is the unit circle. We have, I can slide this to change the angle. So notice, for example, we have pi over 6 here. We learned that this is in radian measure. Pi over 6 is like 180 divided by 6, means 30 degrees. So let me drag this to 30 degrees and we'll see it matches up. There it is. We went to there, there's 30 degrees. When I have an angle of 30 degrees, notice we have an x value here, y value here, and here are the two values. Notice both are positive because we are in quadrant 1 where x values and y values are both positive. Now I'm going to drag this, make it a bigger angle. So now I made it 130 degrees, you can see. So now I'm in quadrant 2. Notice now the x is negative and the y is still positive, and we can see that here. Cosine is negative answer, sine is a positive answer. Go further into quadrant 3. Now I have made an angle of 230 like that. Now we have a point that's here that has both a negative x value and a negative y value. So cosine and sine of 230 should both give negative answers, and they do. Look right there, both negative. Finally, I'm going to go to quadrant number 4. So I've spun an angle of 325 degrees all the way to here. Here's my triangle, has a positive x value, negative y value. And look at here, cosine of 325, positive. Y value, sine of 325, negative. Okay, important to understand those relationships. But the most important thing here to note is anytime you're spinning an angle, all you're looking for by doing sine and cosine is the location of that point. And if you just remember positive x values, negative x values, positive y values, negative y values, then it all makes sense. All these results make sense as to why they are positive and negative. Okay, let's continue with the presentation. And let's use the Pythagorean identity. So here's our first problem. It says without finding the angle theta, find what cosine of theta is when sine of theta is 3 over 5. So we're told what sine of theta is, and we need to find out what cosine is. And again, we don't need to know the angle. We can look at this one in a very simple way. Okay, so we're given sine of theta is 3 over 5. That means we have a right triangle, and sine is opposite of our hypotenuse, so we have opposite side 3, hypotenuse 5. That's easy. Now using that, we can find the last side. Let's say I call this last side x. So I can set up just Pythagorean theorem on that, right? X squared, this side squared, plus 3 squared equals 5 squared. Solve that, subtracting 3 squared, taking square root. That gives us 25 minus 9, which is 16, and the square root of 16 is 4. So we found out that this side is 4. Now, our goal was to find cosine of theta. So again, we don't need to know the angle. We can just set up a cosine for that. Cosine of theta is just adjacent over hypotenuse, 4/5. So that's one way to look at this one, just simply a right triangle. But what about looking at it in the context of our unit circle and the trigonometry we've been looking at? So let's say we had the right triangle, but this time we had this side is 1, so we are now within a unit circle. Our hypotenuse is 1, and we're told that sine of theta is 3/5. Remember that sine in the unit circle represents the y value. So I labeled this y value here as 3/5. That height is 3/5. So now we're looking for this one right here. So we're looking for this side here. Please try using the Pythagorean identity, which looks like this again. Try that now. Solve that. Put what we know in there and solve for what we need and see what you get. Okay, let's check our work. There's a Pythagorean identity. We can replace sine with 3/5 because we know that we were given sine, and we don't know cos squared. We leave it open here. I mean, we assume we haven't done this work yet, right? We're solving this a different way. So we don't know cos squared. Then you go ahead and solve cos squared by doing 1 minus this. That is 1 minus 9 over 25, which is 16 over 25, and then take the square root of that to get this. Answer is the same. It confirms that we get to the same place. However, notice, I mean, it's the same because basically this Pythagorean identity is the Pythagorean theorem. We're just doing the Pythagorean theorem on here just like we did here on this one. But in this one, we had a hypotenuse of 5, and now we have a hypotenuse of 1. So in other words, we said, let's take this triangle and shrink it 5 times smaller. So that means divide every side by 5. So if you divide 5 by 5, you get 1. And then this divided by 5 is 3/5. And then this side divided by 5 gives us 4/5. So it's just a similar triangle to this one, just shrunken down to have a length of 1 here, and it gives us the same answer. So the ratio of cosine doesn't matter on the size of the triangle. We talked about that when we did basic trigonometry. The cosine of this angle here, 4/5, is the same as the cosine of this angle here, 4/5/1. The triangles are similar, therefore the cosine will be the same. Okay, so let's try one like that. Similar problem, but now we're given sine of 50 degrees equals 0.766. So instead of a fraction, I gave you this decimal for sine. So begin by finding the value of cosine. Try that now. Okay, we can think of this one like we did before. We have a right triangle here, and we're told that sine is 0.766, so we know that the y value, this length here, is 0.766. We know the hypotenuse is 1 in the unit circle, and we're looking for this side here. So we can simply do Pythagorean theorem to find, I'm calling this x here, Pythagorean theorem, x squared plus this squared equals 1 squared. That will solve for us x, which is cosine, because cosine of 50 represents the length of x here. So we can solve that and find, so that's Pythagorean theorem. But using Pythagorean identity, which you should be applying as well, same thing. That sine 50 squared plus cos 50 squared equals 1. That's our Pythagorean identity. And we know sine 50 is 0.76. We know that, and you go ahead and solve that. Solving that is exactly what we would do here if we solve that. I want you to really see the parallel between these two. So our answer is this for cosine. Okay, now that we have sine and cosine, we can take this a step further and combine it with the work we were doing last time, where we have one angle in a unit circle and then another angle, and you have to figure out the relationship between those two angles. So if you spin an angle 50 degrees, you'll get this. Cosine means x value, sine means y value. But what if you spin an angle 130 degrees? Your job in B is to figure out, okay, I'm going to spin a 130 degree angle. What is the cosine? That means what is the x value there? And knowing these two values should help you. Try it out. What's the x value at 130? Okay, you should have noticed that 50 looks like this, and if you spin 130, you create the same triangle over here as over here. They have the exact same height and the same length along the x here. So, because this angle is 50, right? And that's why those triangles are the same. So therefore, if it's asking for cosine of 130, it's asking for the x value. If we knew the cosine of 50 is 0.643 positive here, then we know the x value here is going to be that same value, negative, because those triangles are the same, except one is just on the negative side of the x values. All right, hope that makes sense. All right. In C, same thing is happening. We spin at an angle of 230, we end up in the third quadrant. It's asking for sine, which is a y value, so we need the y value produced in this triangle. That y value will be this distance here where I'm moving the cursor now. And that distance is the same as this one, just negative, because we're talking about negative y values. So there's the answer. Try D now. Okay, in D, we spin the angle in the opposite direction, negative, here, so we end up with these two same triangles. It's asking for cosine, means it is looking for the x value. Whether you go positive 50 or negative 50, the x value, this side of the triangle, is the same. Therefore, we have the same answer as we had here. Okay, hope those made sense. They are, in a way, simple problems, but important ones to understand all these relationships in the unit circle. There are more videos to watch. Please get to those now. You can do it.